just to remind you where we were last time, we're constructing a resource theory of non-local correlations. So here we have our non-local correlation in black. It's just a probability distribution over the outcomes given the inputs. And the free transformations in this resource theory are sort of these local pre and post processings, which we can correlate with shared randomness. Just some classical common cause here. And we want to study the resource theory that is induced by this sort of set of free transformations on the resources of interest. So with these free operations, we now want to study what are the possible conversions, what's the preorder over resources, and what are some monotones for quantifying the amount of non-locality. And a first kind of natural starting point would be to think, well, these Bell inequalities, these are the things that you use if you want to witness non-locality. If you just want to know whether or not you have some, all you have to do is check whether any of these Bell inequalities are violated. So a natural conjecture would be that the amount of violation is a monotone, and maybe that if you know the amount of violation of every possible Bell inequality, then that gives you all the information about how much non-locality there is. So let's see if those statements are true. So in the simplest possible scenario where we have two parties, each one does two possible measurements and has two possible outcomes for each measurement, then it turns out you can specify a correlation with just 8 real values. So on the one hand, you have the sort of expectation value for Alice's outcomes when she does the x equals 0 measurement, the expectation values for the x equals 1 measurement, and then similarly, Bob's expectation values for the two measurements that Bob can do. And then you have, and here I'm going to take the outcomes to just be valued -1 or +1, just for simplicity, so that all of these range between plus or -1. Earlier we were labeling them 0 and 1, but it doesn't really matter. And then the other 4 real terms are just the correlations between Alice and Bob's outcomes for each of the 4 possible measurement settings, 0, 0, 0, 1, 1, 0, and 1, 1. So that's all the information you need to specify, sort of marginally, are you more likely to get outcomes 0 or 1 for each possible measurement? And then how are those outcomes correlated between the two parties? And we saw earlier that if we look at just the correlations between the two parties, then we derived a Bell inequality that constrains how correlated those correlations can be. So here, where each of these quantities, each of these outcomes is either -1 or 1, then each of these correlation terms also ranges between +1 and -1. If they're correlated, if they're perfectly correlated, then this quantity here will be +1. If they're perfectly anti-correlated, then one of them will be +1, one will be -1, which means this quantity will be -1. So now, if we take the sum of the first 3 correlators, but then we subtract the correlations in the case where the measurement settings are 1, 1, well, logically, the maximum that this value could be is 1 + 1 + 1 minus -1. So this could get all the way up to 4. But as we argued earlier, if you have that there's perfect correlations between the 0, 0 outcomes and perfect correlations between the 0, 1 outcome and the other 1, 0 outcome, then in the 1, 1 case, they have to be perfectly correlated as well, which means this quantity here will have to be 1 if these other 3 quantities are 1. So in a local model, the maximum that this quantity can be is 1 + 1 + 1 -1. So the maximum value is 2. So that's just another way of writing that inequality that we already derived earlier. It just comes from this kind of pattern of correlations. But now, of course, if I relabel the outcomes, like if I multiply Alice's outcome by -1, that's not going to change the fact that there's a constraint of this form. It's just going to move this negative sign around here. So basically, just up to the symmetries of the problem, I can just put the negative sign could be here, or it could be here, or it could be here. It's still the same basic pattern of correlations where you need 3 of them to be correlated and 1 of them to be anti-correlated. I could also have 3 negative signs and 1 positive sign instead of the other way around. That would just be saying to maximize this, you need these 3 to be anti-correlated and this one to be correlated. So we basically have 8 different inequalities that are all equivalent up to just some relabelings of the outcomes. And these are called the CHSH inequalities, named after the people who first derived these inequalities, Clauser, Horn, Shimoni, and Holt. And so these 8 inequalities, you can prove, are the only non-trivial Bell inequalities for this simplest scenario, where there's 2 parties, binary outcomes, binary settings. So each of these quantities is less than or equal to 2. That's the set of 8 Bell inequalities that single out the local set of correlations. And now we can see that if you ask sort of like, what is the quantitative value assigned by some resource to each one of these quantities do not form monotones. And that's not too hard to see, because imagine that you're here in this particular point here. So this blue set is the local set. And you can see that this point violates this Bell inequality. So it violates one of those 8 inequalities. But it doesn't violate all of them. In particular, look at this one here. It satisfies this inequality because it's sort of on the left of it. So this is a non-local correlation, but you don't see it with this inequality. And now if I just do a relabeling of somebody's outcome, I can flip to the, I can change which of these inequalities is the one that I'm violating. So I've increased the value of this violation. And it didn't violate it at all, but after relabeling, now suddenly it violates the inequality. So it's a kind of trivial way of sort of it's just moving which of these inequalities is witnessing the non-locality by a local relabeling of an outcome. So these by themselves are not monotones then. But there's a natural thing to do. My clicker not working. There's a natural thing to do then, which is to optimize these functions over all relabelings. And then you basically just get one function because they're all equivalent up to relabelings. So basically just find which of them is maximally violated and then take that to be your measure. And you can prove that that in fact does form a monotone, which is kind of preserving our intuition that you shouldn't be able to suddenly violate a Bell inequality more under these local operations or classical correlations. So then the second question, we now have a way to get monotones out of Bell inequalities, but can you completely specify the value of the resourcefulness of a resource via some set of monotones that's defined in this way using those 8 inequalities? So these are called facet inequalities because they're defining the facets of the polytope. So they're like they're picking out the edges of the polytope. They're the tightest inequalities, if you like. And so, as I said, the question we now want to answer is, if we take each of those different inequalities, Bell inequalities defining this local set, and if you know the value of the violation for each one of those, can you then completely infer the relative resourcefulness of resources? So for example, if the local set looks like this, and we have these 4 Bell inequalities, maybe I know that my correlation is out here, so you can see that I violate 2 of these inequalities. I violate this inequality, and I violate this inequality. So if I know sort of how far I am from this inequality and also how far I am from this inequality, is that everything, or is there somehow more information that you need to know? To put it another way, these inequalities, these 4 inequalities, or in the proper case, if I were depicting the whole polytope, there'd be 8 such inequalities. They define the local polytope. So they're necessary and sufficient for deciding if it's local or non-local. That's like the qualitative question, yes or no. But are they necessary and sufficient for quantifying a resource's non-locality? We're going to see in just a few slides that they're not actually sufficient. There's more information in a resource than just how it relates to these facets of the Bell polytope. And so the proof of this is pretty simple. So here again is this kind of cartoon. We have the classical set of correlations. The ones that quantum theory can realize is a strictly larger set. And then the ones that any GPT can realize, this is like the maximally non-local set that's logically possible. And as we said, we have this kind of quantity here that if I draw some level curves for this functional, well, it assigns value 2 to all of these resources. So that's the local bound, right? You can't be any larger than 2. The quantum set can do better. So the maximal quantum violation of this is 2 square root of 2. That's sometimes called the Tserelson correlation, named after the person who derived that. And then the maximal GPT possible value here, as we said, is 4. There's no way for this to be larger than 4, just as a matter of logic. And so now let's focus on 2 particular points in this space. So one of them is that Tserelson correlation I mentioned. It's the maximal quantum violation. So here, it assigns to each of these correlators these particular quantities. And if you just sum these 3 and then subtract off this one, you get 2 times the square root of 2. So that's this point up here. And for that state, these marginals are 0. So for both Alice and Bob, they're equally likely to get either outcome, but those outcomes are correlated in this very strong way. And then the second correlation that we're going to consider has the exact same correlations between their outcomes, but Bob's outcomes are more likely to be the 1 outcome than the -1 outcome. So these marginals are sort of not 0. They're biased towards the positive side. So that correlation in this diagram is off here to the side. And this is something that quantum theory cannot generate. You can prove that in quantum theory, if you have these maximal correlations, then these marginals have to be random. That basically comes from like the symmetry of the maximally entangled state. And you can see that these two correlations, by construction, they have the same value for all 8 of those functionals that we defined, because they have the exact same correlators, and the functionals only depended on these 4 correlators. And yet, I claim that this correlation here, that's this post-quantum correlation, this thing that can't be generated in quantum theory, but it could be generated in some other GPT, is strictly more non-local than this quantum correlation. So to prove that, I need to convince you that it's not possible to convert in this direction, but it is possible to convert in the other direction. Well, this first fact is pretty obvious. If you do local quantum operations and you have classical shared randomness, that can't take you from a quantum thing to outside of quantum theory, just because quantum theory is a closed theory. So there's no way to do quantum stuff to get outside of the quantum set, so this conversion is obviously impossible. That's why I picked this example, because it's very easy to prove that there's no convertibility in that direction. Convertibility in the other direction is also pretty simple. So you can go from things outside quantum theory into quantum theory using local operations and shared randomness. The argument's pretty simple. If both parties multiply their outcomes by -1, well, none of these correlations are going to change, right? Because they're just all being multiplied by -1 squared. But all 4 of these marginals are going to change sign because of this -1 here appearing a single time in the marginals. So these marginals become opposite, and -0 is still 0. So in the diagram, this just flips you to this sort of symmetric point over here. And now if I just mix these two possibilities, so with probability 1/2, I do nothing, and with probability 1/2, I flip both parties' outcomes, which is a local operation, then I can get over to this state, and I'm mixing these two states with equal probability, so I get us exactly to the Searlson correlation that we wanted. So that conversion is possible just by correlating whether or not you do this -1 multiplication of the outcomes. So that conversion is possible, but the reverse is not. Therefore, we see that indeed, this post-quantum resource here is strictly more non-local than this Searlson correlation, even though the two coincide on all of their correlation terms in the probability distribution. So we can see then that the amount of non-locality is a function of these marginals, sort of how likely each party is to get each individual outcome, which maybe isn't completely obvious. And I'll just note, you might think that this is some weird sort of beyond quantum feature, but even if you focus on just quantum theory, basically if you just shift this argument down until it lies inside the quantum set, you can run a similar argument. It's just a bit harder to prove that you can't do the conversion from the sort of center resource outward. And intuitively, when you're moving sort of outward, you're kind of increasing the purity in some sense, like the purity relative to what is possible in any GPT. And so that's kind of why it's more non-local, because you're keeping the same amount of correlation, but you're being more extremal. So that's a kind of intuition. So just summarizing again, the values of these Bell functionals that define the local polytope, they are necessary and sufficient for witnessing non-classicality, but not for quantifying it. So you need to find more monotones then, and we're not going to spend our time doing that, but you can find plenty of monotones in the literature. Here I just want to state a few interesting facts. So when you work out how this resource theory looks, you find that there's infinitely many inequivalent, maximally non-local boxes. So here, for example, let me focus on this little triangle here of the space of resources, because all these other areas are sort of equivalent to that triangle up to symmetry. So if I focus on that triangle, this point here is the maximally non-local correlation that any GPT can generate. That's called the Popescu-Rohrlich box, or the PR box. It's the one that gives you a violation of 4 for these CHSH inequalities. This point we said this point here is the Tserelson correlation. This point here is this point, which is like a free local resource, and this is another local resource. But this one's extremal and this one's not. And if I just plot the sort of quantum correlations here, this curve here, this is what it looks like a little more carefully. This is kind of a cartoon, but this is actually like a calculation. So these are the extremal quantum correlations you can generate. And you remember we did that proof of Hardy's theorem? The correlation in that proof is exactly this point here. And the correlation that quantum theory uses to violate the CHSH correlation with the CHSH inequality with a 2 square root of 2, that's that Tserelson box, that's this point here. And all of these points along this edge are sort of extremal correlations that quantum theory can generate as you vary over the different entangled states and the different measurements that you're doing. And we can also plot 2 monotones in this space. So here's that CHSH monotone that just tells you how far are you outside of the local set. So as you go higher and higher in this set, you get a larger and larger value of this blue monotone. And then the second monotone, it's measuring sort of how close are you to this edge of the diagram. So like how pure are you in this GPT sense. So this monotone increases as the angle sort of sweeps upwards. So it's maximal on this edge and it's minimal down here at the free set. And we can see then that every single point on this set of quantum boxes is inequivalent to every other. Because as I move along this curve from left to right, I'm decreasing the value of this blue monotone, but I'm increasing the value of this yellow monotone. And so you can't move in either direction along this curve, because to do so would require one of these 2 monotones to be increased. So these 2 monotones are sufficient to tell you that all of these resources are inequivalent. And because they're sort of extremal, there's kind of nothing outside here that can move down to any of them. So they're all maximally non-local. So we now have a resource theory of entanglement, and we have a resource theory of non-locality. Well, the natural thing is to ask, how are these related? Because we're kind of used to using entanglement to generate non-local correlations. So how do these resources relate to each other? How do they transform into each other? That's the next question. First, are there any questions? All right. So when people started to ask this question, I think about 15 years ago, they realized that something odd was happening. Sometimes having more entanglement meant that you couldn't generate as much non-locality. So to put it a bit more formally, what they were finding over and over was that measures of non-locality typically could be maximized by partially entangled states, but could not be maximized by maximally entangled states. Now that should sound very weird to you. Like why do you need entanglement to generate non-locality, but somehow having more of it penalizes you? So people were very confused by this. There were a whole bunch of papers, and this came to be known as the anomalies of non-locality. So here's an example. Remember that pattern of correlations that we saw when we proved Hardy's theorem? So Hardy's proof of non-locality? That was using a partially entangled state. We had the state 0, 0 plus 0, 1 plus 1, 0, which is not a Bell state. It's not maximally entangled. And it turns out that that was not an accident. If you tried to use a maximally entangled state to generate that pattern of correlations that we saw in the Hardy proof, it's just not possible. So remember, that pattern of correlations was for 3 pairs of the settings, the probability is equal to 0. And then for the 4th pair of settings, the probability was non-zero. That was sort of the key thing that led to that proof of Hardy non-locality. And you just can't generate this pattern of correlations with a maximally entangled state. I didn't want to spend 5 or 10 minutes on this proof, so I'm just going to leave it in the lecture notes. The proof's not too hard. It's just kind of 2 pages of algebra. But you go through that algebra and you see that no maximally entangled state can generate that pattern of correlations. So this is a kind of non-locality that you can only generate if you have less entanglement, strictly less entanglement. And there's a lot of examples of this. So this is not sort of a unique to the Hardy argument. There's maybe 15 or 20 different measures of non-locality, which can only be maximized by partially entangled states. So here's just a few examples. If you ask sort of what is the optimal quantum state to generate non-locality as measured by the probability of getting a Hardy proof of non-locality, that's the example I just gave, or the violation of a particular sort of Bell inequality called a tilted Bell inequality, or the extractable secret key rate. So this is a kind of measure of non-locality that's related to some actual operational tasks that people care about. Or if you want to find just the sort of relative entropy distance from the local set, etc. So for all of these different ways of measuring non-locality, what you find is the optimal state, if we're focused here on 2-qubit pure states, for example, the optimal state in every case is somewhere in the middle here. It's never this maximally entangled state. And moreover, the optimal state is different in each of these cases. So as I vary over each of these, sort of this optimal state is moving around. So it kind of seems like the amount of entanglement just has nothing at all to do with the amount of non-locality. And that seems odd. However, the resolution is actually quite simple. The resolution is that in this context, when we're talking about a Bell scenario, we've been using the wrong resource theory for quantifying entanglement in this context. So there's actually more than one resource theory you can use to study entanglement, and which one you use depends on the particular scenario that you're studying. So LOCC is not the only reasonable choice of free operations for quantifying entanglement. You could also quantify entanglement using the exact same resource theory that we did for non-locality, these local operations and shared randomness. And it might already then be kind of intuitive once you recognize this, that using sort of a consistent way of measuring entanglement and non-locality is going to lead to a resolution of this anomaly. So how do we see that this is a resource theory of entanglement as well? Well, first of all, let's just note that the LOSR operations are a strict subset of local operations in classical communication. So here I have an entangled quantum state, and an arbitrary LOCC operation looks like this. So you have all these local transformations, and in between each local transformation, you can communicate back and forth between the two parties. So there's no kind of closed diagram that shows the most general LOCC operation, because you can keep transferring information back and forth. And here I've included the shared randomness. You don't need to include it because you could always generate it via this classical communication. But I just want to make it extra clear that this most general LOSR operation is a subset of these LOCC operations. So in LOSR, the local operations, again, just transform these quantum states into other quantum states. But we can correlate our choice of local operations with this shared randomness here. And so this is the most general LOSR operation, from a quantum state to a quantum state. So we're basically applying the same set of free operations, but now the resources of interest are no longer correlations in the sense of black box correlations. They're rather bipartite quantum states. But the basic methodology is all the same, and the set of free operations is all the same. And this definition leads to the same qualitative divide. If you ask sort of what is free and what is non-free in this LOSR resource theory, it's still separable versus entangled. So you can see that sort of immediately, because the most general bipartite state you can construct with local operations and shared randomness. Well, local operations just give you product states, right? Here's the most general local operation. And now we can correlate our choice of local operations with this shared randomness. So that, writing it out algebraically, it's just some classical probability distribution that we're using to correlate these product states rho I tensor sigma I. So this is the most general state you can prepare in this resource theory. And this is, of course, just the form of a separable state. So we see that the LOSR free states are exactly the separable states, which means that the LOSR non-free states are exactly the entangled states. So this reproduces that sort of qualitative divide that the LOCC resource theory gives. However, when we move to the question of quantifying resourcefulness, we're going to get a very different set of quantification, different monotones, a different preorder in this LOSR approach than we did in the LOCC approach, because the conversions that are possible are going to be a lot less using this smaller set of free operations. So like in any resource theory now, one resource is less resourceful than another. Sorry, it's at least as resourceful as another, which in this case means at least as entangled as the other, if and only if there's a free conversion from the first to the second, relative to the free operations, which we've now changed from LOCC to LOSR. And before we develop that resource theory further, you should ask yourself, of course, well, which resource theory is the right one? You don't want to have 100 different resource theories to quantify a single object of interest. So the essential starting point you should ask yourself when you're constructing a resource theory is, what are the right set of free operations to capture the kind of quantity that I'm interested in? But of course, that will depend on the situation. And in this context, you can kind of see the relevant features of the situation that determine which resource theory you should use. So if you're trying to study entanglement as a resource for generating common cause correlations, then you would allow classical common causes for free. So for example, if I'm in a Bell scenario where I have spaceless separation, well, there's no sense in which classical communication is going to be free, because that would sort of violate the relativistic assumption that things are at spaceless separation. And so then if you're studying something like key distribution or randomness generation that is built around a Bell scenario, so these scenarios use correlations from sort of distributed parties who are far apart, then you're going to want to use this approach where classical communication is not free. So you use the LOSR approach. In contrast, if you're studying something like teleportation, well, then you know that to use your entanglement as a resource, you need to have classical communication between your parties. So this would be a context where it's more natural to use the LOCC approach, because you need to have access to classical communication to use your entangled states in that way. And similarly, if you want to study sort of quantum Shannon theory, so quantum communication, then if you're trying to sort of quantify how much quantum communication is there, well, then typically you'd imagine that the classical communication is free. And so, again, you would use this LOCC approach. But in each context, you have to ask yourself sort of, which is the relevant set of free operations? That's kind of a question that you need to answer by thinking about the physics you're trying to understand. And it might not be either of these, right? These are just two particular sets of free operations motivated by some particular kinds of circuits and scenarios and physical situations of interest. But if you're working in a condensed matter system or something, or if you're working in cosmology, it's not clear that either of these is the right set of free operations. So you have to build your own entanglement theory. Maybe it will be one of these two, but maybe it won't. And I think this is not very well appreciated, that outside of the context of sort of quantum communication, this traditional approach to quantifying entanglement is not somehow uniquely the right one. You have to kind of always ask yourself, where do these measures come from? Am I actually using measures derived in the right resource theory? So the key step in any resource theory is just getting the free operations right. Obviously, that's the key step because it's the only non-trivial step. Everything else is derived from the free operations. So you better get the free operations right. So with that, let's now develop this resource theory and see how it compares to the other resource theory of entanglement. So now I'm going to try to remember to always qualify which type of entanglement I mean. So I'll call it LOSR entanglement. And afterwards, we'll see how this resource theory resolves those anomalies of non-locality. So consider, for example, you have a bipartite state, the most general free transformation, local operations, and then we can correlate those with our shared randomness, as we already mentioned. So each of these channels here is just a local channel. So this is a product of two local channels, EI tensor Fi, and then we're mixing those together using this classical randomness. So this is the most general transformation on a bipartite state. And we can prove from this an analog of Nielsen's theorem. So remember, Nielsen's theorem told us a necessary and sufficient condition for LOCC conversions between two bipartite pure states. This is this analogous thing, but for LOSR conversions. And it looks kind of similar. A pure state psi can go to a pure state phi if and only if there's some new pure state xi such that the vector of squared Schmidt coefficients, when you sort them from largest to smallest, for psi is equal to the sorted vector for the tensor product of phi and xi. So it looks similar, but now we have this extra state xi here. And we don't need to focus too much on this condition, because this isn't a quantum information theory course. I'll just note that the proof is not too hard once you realize that randomness cannot help you ever convert to a pure state. So if here we're talking about conversion to a pure state phi, then you can't use any sort of mixed procedure. Anytime you have some mixedness, then this final state would be a mixed state, not a pure state. So you can basically ignore the classical correlations between the two parties, and you only need to consider sort of local actions, like unitaries or traces or introducing some ancilla systems. And that simplifies the proof a lot. So let's just use this condition, and we can use it to prove that for 2-qubit pure states, there's actually no non-trivial conversions that are possible within this resource theory. So in LOCC, we saw that you could sort of convert between any more entangled state to any less entangled state. Like you could decrease that theta variable sort of arbitrarily. But here, there's no non-trivial conversions. And the proof is pretty simple using that condition on the previous slide. So think about the number of non-zero Schmidt coefficients in a bipartite 2-qubit entangled state. So at most, there's 2 non-zero terms, right? It's like lambda 1, 0, 0 plus lambda 2, 1, 1. And if it's an entangled state, then there's exactly 2 non-zero terms, 2 non-zero Schmidt coefficients. And then similarly, the Schmidt rank of the phi state, if it's an entangled state, then it has exactly 2 non-zero terms. So these vectors of squared Schmidt coefficients have exactly 2 non-zero entries. So this condition on the previous slide then, for convertibility from psi to phi, well, for this to work, it's going to have to hold that this vector here, which has 2 non-zero entries, has the same number of non-zero entries as the vector on the right-hand side. And this vector here has 2 non-zero entries. When you take the tensor product of 2 real vectors, it just multiplies the number of non-zero entries. So 2 times the number of non-zero entries in this vector here has to equal 2, which means that this number of non-zero entries for this Xi state has to be 1, while the only sort of vector for a normalized quantum state in Schmidt form has got to have a Schmidt coefficient of 1, just by normalization. So this vector here is just a single vector with a single entry, which is 1, which means basically we can ignore it. Tensoring by this vector does nothing. So this lambda psi vector has to just be equal to the lambda phi vector. So the only way to have a conversion from psi to phi is for the vectors of Schmidt coefficients to be equal, which means that those states are basically equivalent. They're right, two states that have the exact same Schmidt coefficients are equivalent up to local unitaries, just local basis changes, right? And local unitaries are, of course, free in this LOSR resource theory. So 2 such states have exactly the same entanglement. So if you give me any 2 pure states, then they're either the same amount entangled or they're completely incomparable. There's never one that is more entangled than the other in this simple case of 2-qubit pure states. They're always incomparable or equivalent. And so here, if we write these sort of inequivalent canonical form for all of these, this is like the equivalence classes of 2-qubit pure states, both in the LOCC and in the LOSR resource theory. And we can plot those states here again. Every point in this space, except for this free point, which is totally free, is unordered. There's none of them that are more, strictly more than any of the others. So clearly then we need at least 2 monotones to form a complete set for these states. So for example, you could just take one monotone that monotonically increases as you go from left to right, and then another one that monotonically decreases as you go from left to right. So they have the opposite order, and they tell you that every point here cannot be converted to any other point, because to do so you'd have to increase one of these 2 monotones. And in fact, you could take this first monotone here just to be one of the LOCC monotones, like the von Neumann entropy of the marginal state, because every LOCC monotone is a valid LOSR monotone. That's kind of clear because, remember, the set of free operations for LOSR is a strict subset of the LOCC ones. So if a conversion is impossible relative to LOCC, then it's also impossible relative to LOSR. And so this is just a generic feature. If you're ever comparing 2 resource theories, and one of them has a strictly smaller set of free operations, then that means all the monotones from the other resource theory are also valid monotones. But there's more monotones in the second resource theory, as we see here. You need a second monotone to capture all of the information about the preorder. Yeah.
I have one question about the proof. So the proof assumed that the 2-qubit pure state is entangled, right? So that the Schmidt rank is 2, not 1.
That's right. So there's sort of...
When you say all 2-qubit pure states are LOSR incomparable, is this only all 2-qubit inseparable pure states?
Yeah, thanks for clarifying. So this point here, which is product, has a single Schmidt coefficient, and it's obviously free. So the monotones here, there's like a singular point here where they need to assign a lower value than they do for all of the other points on this line. Yeah, so this a bit more carefully stated. All entangled 2-qubit pure states are LOSR incomparable or equivalent. Yeah. Is that your question as well? Yeah, thank you. And so we can already start to see that once you're using LOSR in both the study of entanglement and the study of correlations in Bell scenarios, then things start to look more analogous. So we saw just a second ago that all entangled pure states in the simplest scenario, 2-qubit scenario, are LOSR incomparable or equivalent, just like in this space of correlations, we said that all of the convexly extremal quantum boxes in the simplest scenario are LOSR incomparable. So in both cases, we have this sort of infinite continuum of maximally resourceful objects. And in both cases, you can witness that with just 2 monotones. Now, I want to be clear that once you go to sort of higher dimensions, or you study mixed objects, not just pure objects, then the preorder is a lot more complicated, and there's lots of conversions that are possible. So it's not always this sort of unordered set of resources. But once you go there, then you need more monotones, and everything gets more complicated. So now, how can we use these insights to resolve the anomalies of non-locality? Well, we just saw that there's infinitely many incomparable, maximally LOSR entangled states, even in this simple scenario. So different such states are going to be optimal for different tasks. Each one is maximally resourceful in some sense. So you expect there's something you can do with it that you can't do with any of the other resources. And indeed, that's exactly what we were seeing with each of these anomalies. Each anomaly of non-locality was exactly picking out some particular operational task that could be optimized by the associated maximally LOSR entangled state and not by any of the others, including the maximally LOCC entangled state. So, in other words, more entanglement does always help you if you're measuring it sensibly. If you're using the LOCC measures, it looks like you need less entanglement. But in the LOSR approach, it's always a maximally LOSR entangled state that's giving you the optimal probability of success. And in fact, you could take the operational probability of success at each of those tasks and just define that as a valid LOSR monotone peaked at the associated maximally LOSR entangled state. So if we have this set of states again, and we find that sort of this is the optimal state for generating some secret key rate, well then if you just say, give me any state you want and optimize under all LOSR operations, what's the best secret key rate I can generate, well then by definition, it's going to be a monotone. It's something you can't increase under LOSR operations because you've defined it to be optimized over the LOSR operations. So here's just kind of a cartoon of what the extractable secret key rate might look like as a function of the amount of LOSR entanglement. And it's maximal at this maximally entangled LOSR state, which is the best one for extracting secret key. This is just a cartoon, not actually a calculation. And if you do that same computation for a different one of those tasks, like computing a Hardy proof of non-locality, then you'll get some other curve which is maximal at some other optimal state. And the maximally entangled state might be useful for some of these tasks, the maximally LOCC entangled state. It's just not as useful as these optimal states. So in summary, LOCC entanglement is not very closely related to non-locality, but LOSR entanglement is closely related to non-locality. And each one of these many different observed anomalies of non-locality was just nature trying to tell us that we were quantifying entanglement in an incorrect way. But it's just LOCC entanglement theory was developed first, and it was kind of just taken to be the way, the sort of unique way that you quantify entanglement. And so people didn't really think to question it and to come up with other ways to quantify entanglement. And this is a great example of how sort of realist commitments can impact pragmatic considerations. So if you have some kind of interpretational or metaphysical commitments, that impacts even this way you go about answering really practical questions like quantifying how much of a given resource you have. So for example, imagine that you believed really that Bell's theorem is trying to teach us that nature has non-local causal influences. So you really believe there's some superluminal causal influences. Well, then if you were trying to build a resource theory of sort of correlations in such a scenario, you might do something different from what we did in this course. You might, instead of trying to quantify sort of how non-classical is the common cause, you might try to quantify how much hidden causal influence is there here. That would be a very different kind of resource theory of non-locality. And it would have different free operations where I don't know what they would be, but they presumably would not forbid classical communication. If you believe in superluminal causal influences, it's usually because you want to imagine that all the systems involved are classical. So this would be a very different kind of resource theory. Whereas in contrast, if you're committed to locality, so you really think that the causal structure has to somehow be a common cause, then you believe that the only relevant processes in such an experiment are common cause processes. You're not going to allow any non-local causal influences, classical or otherwise. And in order to have, what am I saying here? Then the thing that you study in such a scenario, you're going to allow classical common causes for free, so that the resources are precisely those things which require some non-classicality in the common cause. And this is actually the line of reasoning that led researchers to introduce this LOSR resource theory and to use it to resolve the anomalies of non-locality. They were saying we should really be committed to locality, in which case, why are we allowing classical communication in quantifying correlations in a Bell scenario? And that was the line of reasoning that led them to propose this new LOSR resource theory. So it was really these metaphysical commitments that led to these pragmatic considerations. And if you take this seriously, then you might notice that the language of calling these sort of non-local correlations, like a resource theory of non-locality, is kind of a problematic language. It suggests mentally that somehow there is some causal influence, non-local causal influence. So it'd be better to call this a resource theory of non-classicality of common cause rather than a resource theory of non-locality. The thing here that is resourceful is precisely something that goes beyond a classical common cause process. So this would be like better terminology if you take this idea seriously. And once you're thinking in this way about parties who are sort of at space-like separation or otherwise in some sort of common cause arrangement, so even if you're not at space-like separation, if you're really sure that there's no causal influences between the two parties, then you can apply the same exact logic to any type of process, not just to black box correlations or entangled states. You could also apply it to other things like steering or distributed measurements or distributed channels. So let me say a bit more what I mean by that. And this is what you might call the type-independent resource theory of LOSR. So we're just going to apply the same logic to introduce a resource theory that isn't focused on a particular type of resource, but rather studies sort of all different types of resources you could consider. So the first type of resource we've already studied is a quantum state. Well, we've also talked about how you can convert that quantum state to black box correlations just by doing local measurements. So that was the second kind of resource that we studied. But if you just do local measurements on one side, this is also a type of resource you could study. It's just a process with a quantum output on Bob's side and a classical input and a classical output on Alice's side. This type of process people often call a steering assemblage. It's the exact type of process that Einstein, Podolsky, and Rosen talked about when they talked about steering, right? You do measurements on one side and you consider the quantum state on the other side. And you consider multiple different possible measurements. That's the whole point of quantum steering. So these are like processes you would study in a steering scenario. If I instead want to do something more like teleportation, where I bring in some quantum system together with my entangled state, and then I measure locally the two halves of it. So this is a local measurement in Alice's side, and here's a local measurement on Bob's side. But if I consider these systems being measured here as like open quantum inputs, well, this overall process, this is just a measurement process on a bipartite system, right? So you might call this like a distributed measurement. So you could ask, what if Alice and Bob are far apart, what kinds of measurements can they do on their systems? Well, if they only have LOSR operations, then, as you might be able to guess, they're not going to be able to do sort of any entangled measurements. They're only going to be able to do separable measurements. But then if you have an entangled state as a resource, you can use it via some process like this to generate an effectively entangled measurement on these two distributed systems. So this is like a distributed measurement process that people also study in quantum information. And in fact, there's kind of, as you just vary the different types of these input and output systems, there's like 15 different types of processes that you can study. And all 10 of these have been studied in the quantum information literature. These have to do with like teleportation scenarios. These have to do with steering of different types. This is just a generic bipartite channel, right? You can ask how sort of non-classical is some bipartite quantum channel? Do I need entanglement to generate some particular channel? Yes or no? And so for all of these, we can apply this LOSR approach and compare the relative resourcefulness of all these types of resources. And in every case, the free set is very simple to define. It's always just the ones that you can simulate with local operations and shared randomness. The only difference is in each case, these local operations need to have the appropriate input and output types. So if it's a quantum state, then these inputs are trivial and these outputs are quantum systems. If it's a Bell scenario, then all 4 of the inputs and outputs are classical systems. So you're just ranging over the types of local operations that are relevant. But everything else remains the same. So if I specialize to states, we get this diagram here, which is the set of separable states. If I specialize to boxes, then this is the set of local boxes. If I specialize to those steering objects, called steering assemblages, these are exactly the so-called unsteerable assemblages, the ones that are classically explainable by a classical common cause. If I focus on distributed measurements, sorry, these should be classical wires, then this is the set of classical distributed measurements. So in each case, basically, the set of objects of interest that are uninteresting and freely preparable is just the LOSR-free operations of that type. And that works for all 10 of those things that people have studied. And there's even some types that people haven't studied yet. Most of these are sort of motivated by some specific sort of quantum information processing tasks. The remaining 5, I guess nobody has seen a sort of specific operational way to motivate. Maybe there is one that just hasn't been found yet. Okay, so we already talked about LOSR conversions from quantum states to quantum states and from boxes to boxes. These are what those most general conversions look like. But it should be clear by now that you can also apply this logic to sort of type changing operations. You can ask sort of if you're given a process of some arbitrary type, where these might be classical, quantum, or trivial, then you can convert that in the most general way. The most general way to convert that to some other process, potentially of different types, is just always take these local pre and post processings and then correlate them with shared randomness. And now if the types of these starting resources, inputs and outputs, are different from the final resources, inputs and outputs, then that gives you exactly a sort of type changing free operation. And for each case, you can just figure out what type of pre and post processing you need here just by looking at the nature of the inputs and outputs. In some cases, it'll be like a set of quantum measurements. In other cases, it'll just be some stochastic map from the inputs to the outputs, or some combination of those two. So as a simple, really obvious example, if you give me a quantum state, a bipartite quantum state, the most general conversion to get some correlation is not just to do local measurements, but we can correlate those local measurements with my shared randomness. So this is like the most general conversion from a state-like process to a box-like process. And if I have a channel-like process where all of these are quantum systems and I'm trying to convert it to a distributed measurement, well then, here again, I'm just drawing the most general process, but now I specialize to the case where these final outputs are classical outcomes, because that's the distributed measurement type of resource. It's a map from quantum channels locally, quantum systems locally, to classical outputs locally. And so clearly that's just a sort of speed run of this, but I hope that it gives you the flavor of this type of resource theory. And once you consider all of these within one unified resource theory, well, now you have this massive, complicated pre-order over all these different types of resources, right? Like, I could talk about, like, starting with a quantum state, like the singlet state, what types of distributed measurements can I generate from it? So here's one possible conversion. If I take that singlet state and I do local Bell measurements on it, well, clearly this is a valid distributed POVM that I can generate via local operations on the singlet. So this is a valid conversion. And in fact, if you compute what this measurement is effectively, it's just a Bell basis measurement on these two systems. So you can generate a sort of entangled measurement on two separated systems by consuming a singlet resource. So that's mapping an entangled state into a sort of distributed entangled measurement. That's one possible conversion. It's less obvious, but I'll prove it on the next slide, that if you're given this entangled measurement, you can actually turn an entangled measurement back into an entangled state, at least in this case. You can convert this thing back into the singlet, which isn't at all obvious until you see the proof. If you're given the singlet, another thing you could do, you can convert it to one of these particular steering assemblages, where you just measure it locally in one of the X, Y, or Z bases. That's an LOSR operation. It's a local operation on the singlet, so that's a possible conversion. If I then just coarse grain over the Y outcome, or rather, just imagine you never do the Y setting, so you never feed in the Y setting. Well, that's something you could do with one of these processes. So you can map this to sort of a coarse-grained version of this assemblage. If I take this assemblage and then measure the quantum state on the other side in the appropriate sort of rotated by 45 degrees basis, well, that's exactly the way that we saw in the CHSH scenario, that you get the Searlson correlations, the maximal quantum violation. So this is like a box-type correlation that you can get from this assemblage, which you got from this assemblage, which you got from the singlet state, which maybe you got from this distributed measurement. So right, you just have this massively complicated pre-order of all these different types of resources, and you can study which ones are convertible into which others. Of course, if these conversions are all possible, then if you close under transitivity, then all of those conversions are possible. And you can imagine this gets very, very rich and complicated to study. But it gives you a lot of information on sort of what you can and can't do with quantum information resources. So the final thing I'll say is just proving that last fact, that this entangled measurement can be converted back into an entangled state, because it's kind of cool and it's super simple proof. So imagine you have any process of any type here with a quantum output wire. My claim is that if you do a Bell basis measurement on that system, and you view this kind of wire here as a free open wire, this process here, which now has an extra quantum input and a classical output, is in the same LOSR equivalence class as the original channel E. It's not at all obvious, right, that you could convert some arbitrary quantum channel to something only with classical outcomes without losing the non-classicality. You might have thought that somehow you're kind of dephasing things, so you're going to lose non-classicality. But the fact that we also have this quantum wire here is what's going to save us. So in particular, to see that these are in the same equivalence class, all we have to do is remember how teleportation works. So imagine, notice all of this is local operations on Alice's side of the channel. Imagine Alice feeds in the maximally entangled state here, and then takes this classical outcome of this Bell basis measurement and does the appropriate correction operation that we saw in the teleportation protocol. This whole thing here is just exactly that teleportation circuit we saw, where you start with an entangled state, you do a Bell basis measurement on some input system, and so this input system gets teleported to this output system after the correction operation. So this whole thing is an effective identity channel from this quantum system to that quantum system, which means that this whole thing is just equal to E again. So here, starting with E, I apply this Bell thing to get a new resource, then I apply this red set of processes to get back to E. So these two resources, E versus this composition process, this composite process, are in the same LOSR equivalence class. In fact, here you can see they're even in the same local equivalence class. They're locally equivalent. So that's not really obvious, but the proof is super simple. And it means that if I go back to that example we had here, well, if I start with this process, then I can just do that teleportation trick here to basically get rid of that Bell measurement. And I can do that on both sides, leaving me back with the singlet state. So that's kind of cool, converting from a measurement to a state, which is not something we're used to thinking about. That's all that I want to say about resource theories. If you're interested in any of this stuff, here's a few references. I don't have a specific reference for LOCC entanglement theory, but that's like a very traditional topic, so you can just read about it in like any quantum information textbook that's up to date. Okay, we have a few minutes either for questions or we can, yeah, question.
Are the two qubits entangled states asymptotically convertible? The many copies of them?
In LOSR?
LOSR.
I don't think that's been studied yet. This resource theory is relatively new, and I don't think people have yet gotten to study asymptotic convertibility. There's kind of a lot of questions still to answer about that resource theory. Yeah, LOCC has been around for like 2 or 3 decades, so it's much more developed. But it's a good question. I think it's known that there's not catalysis in the LOSR resource theory, at least in like the simplest cases, but that's a separate question.
Is there a catalysis for LOCC?
I don't know actually, but it's known. It's something that's been studied. Any other questions? Yeah.
By that purifying argument that you can pick any state can be just seen as a pure state on higher, shouldn't we be able to generate entanglement from LOSR as well, like freely, like just by restricting the system, or like you can pick a mixed. I'm sorry, I don't know exactly. I was just thinking you maybe could generate more entanglement freely, right? By restricting.
So I'm not sure I've understood the intuition, but so purification is kind of a mathematical fact about a state, that there could exist some larger state. It doesn't necessarily mean that the density matrix you have is actually coming from such a pure state. So for example, if the way I got the density matrix was like locally doing some state preparation and then flipping a coin and conditioning on it, it's not like there's some physical operation that suddenly makes that preparation procedure part of a larger entangled state. So I think, yeah, maybe it's just because it's not a physical operation that you can't sort of suddenly get to that larger entangled state.
Okay, makes sense.
All right, any other questions? Cool. I don't think we really have time to go on. So the final lecture tomorrow is going to be on interpretations. It will be very fun. I didn't think we'd get here, but we've managed, which probably means I was going a little too fast. But it will be a fun lecture. And it probably will run a bit over, just because I'd like to talk about 3 different interpretations, and it probably takes more than 20 minutes each. So if people can't stick around after, that's fine. But I'll do collapse theories, and then Bohmian mechanics, and then many worlds at the end. So you have to stick around if you want to hear me complain about many worlds. It's okay, I'm going to complain about all of the interpretations. The conclusion is going to be that none of them are especially compelling. Yeah. Okay, thank you.